So for this tutorial, you should have switched from the simple model to the full model in the general controls section. And what you should see is the ability to change the urea permeability in the outer modella, as well as change all the permeabilities within the inner modella. So the cocoa and rector model is a theory that attempts to explain that salt reabsorption in the inner modella is actually mediated by urea accumulation. So as we said last time, the fluid entering from the proximal convoluted tubule is isotonic, and as it moves down the descending limb, the osmolality increases as water moves out. So again, we're going to change the water permeability here, both in the outer modella and within the inner modella. We're now going to quickly move on to the thick ascending limb, which is where this black writing is. So anything in black writing is the outer modella, while the blue writing is all the inner modella. So at the thick ascending limb, salt is continuously being pumped out, making the fluid inside the tubules increasingly hypotonic, while the surrounding interstitium increases in osmolality. And remember, the thick ascending limb has a lot of salt pumping through the sodium-potassium ATPase, as well as having a transporter on the apical membrane called the sc2 transporter. It's also important to understand that there's no salt permeability within the thick ascending limb. So we're going to change the salt pumping to around 200. And as you can see, the changes are starting to be made. When the fluid enters the collecting duct, it is hypertonic and contains a small amount of urea. And as it moves down the collecting duct, in a state of antidiuresis, so as in the presence of vasopressin, water moves out through aquaporin 2 into the surrounding interstitium. So what you should have done is change the water permeability again to around 100 here, and in the inner modella as well, it should change to 100 as well. Vasopressin also rapidly increases the urea permeability in the inner medullary collecting duct, so just in the inner medullary collecting duct, through increases in phosphorylation and the accumulation of urea transporter A1. So this allows the urea to flood out of the collecting duct and equilibrate with the interstitium. So let's change the urea permeability here to 12. There's therefore a greater salt concentration in the fluid of the thin ascending limb than in the surrounding interstitium. So therefore salt moves down the concentration past the highly permeable walls in the thin ascending limb, which will be changing to salt permeability to around 10, into the surrounding interstitium. The cocoa and rector model presumes that both the thin ascending limb and descending limbs are both impermeable to urea. So what you should see is again an increasing osmolality as you go down the descending limb, which is all permeable to water. And as it moves up the thin ascending limb here, this has a high permeability to salt, so salt moves outwards. And in the thick ascending limb, salt is being continuously pumped out into the surrounding interstitium. And the osmolality should increase down the interstitium from the corticomedullary axis to deep into the medulla. And actually what you could try is decreasing the inflow to see these changes to around 30. And again, there's around a 200 milliosmol difference at each level between the ascending limb and the interstitium. It may take a while to see the changes within the inner modella. So if we just click this button here, we should see these changes occur. So here you have the simple current multiplication button and the cocoa and rector model, which have preset settings and will allow you to see these changes occur naturally in front of your eyes.